Hello. Albert Einstein said among the most difficult problems in all of physics is the Earth's magnetic field. I'm Michael Doran, I'm a California attorney, and I'm here to argue that the Earth's magnetic field is actually among the most difficult problems in all of biology. Hello, and welcome to Convergence. The name of the show is Convergence because technology is advancing rapidly in numerous fields, and when they come together, they speak to the other fields. And today I'm going to talk about NOAA's forecast of La Nina and what it really means to the climate change debate. I'm a California attorney, and obviously I'm not a climatologist, I'm not a physicist, I'm not a biologist. My background basically is mathematics and as working as a lawyer. I also have some training in the military with electronics. About 25 years ago, I started to participate in numerous bulletin boards and listservs and so forth. People who were debating, scientists who were debating the climate change that was occurring, obviously, and some people were taking a skeptical position about whether global warming was occurring, and some people were warmers and saying greenhouse gases caused what was being seen. Now, fewer and fewer people are debating about whether or not change is occurring, and the natural inclination is to say that it has to do with CO2 as a greenhouse gas. That's the state of the science right now. But I'm talking about a totally different mechanism. My view is that CO2 is much more interesting in clouds, in cloud droplets, as they go in phase change from water or liquid to ice. And that ice or cirrus clouds, particularly, are much more important in terms of heat trapping and the dynamics of what's going on in the climate system, and also that this is in the context of electrical fields. I'm going to talk again about this paper. When I started to think about this, that I read over 20 years ago, it was a paper published in China about cryogenics, which is just this idea of freezing bodies and seeing if you could regenerate life later after it's been frozen. And probably the biggest story about that was a baseball player who had his head frozen. He was a famous baseball player, and there were jokes made about it, but Ted Williams, he's a 400 hitter and very famous player. And but this study in China fell under this category of these studies that had to do with freezing bodies and maybe regenerating them later. And what the study did was it took a kind of an acid that is typical and used for experiments, and they put drops of this acid on a metal plate, and then they had an anode and a cathode, which is basically a positive charged end and a negative charged end, and they created this field, and then they enclosed this weak acid in a glass tube, and then they dropped the temperature of the droplet that was in this field. And they observed, and what they saw is that compared to water, which will freeze in circular patterns, snowflake, different patterns in a snowflake, what they found is that the droplet in the field froze like a Christmas tree. And why shape matters, why the asymmetry of the freezing matters, is because then you start to have these water molecules, right? So the water molecules go from hydrogen and oxygen, and they're moving with respect to themselves. There's a force called the van der Waals force, which is this idea that water is polar, weakly polar. And so the hydrogens, my pinky and my thumb, tend to lose a little bit of the electron orbital and then have a positive charge. And the oxygen tends to have a negative charge. So the molecules interact with each other, positive to negative, negative, positive. And liquid is just kind of this, well, it's a fluid where these charges are attracting each other weakly and they move around. And when you have gas, water gas, and they come together and form water, they give what's called a phase change energy. And that phase change energy is basically a delta energy, a energy that causes a vibration in the water droplet that bounces off other molecules and heats up the air. And that's really important in meteorology because the heated up air will tend to expand, and when it expands, it rises. Well, the same thing happens with the phase change from water to ice. And so you get an order of a solid, and it's giving a phase change energy to the air, and it's causing it to rise because all the other molecules like oxygen or nitrogen or carbon dioxide in the gas form, all those things will trap heat, cause the air to warm up, not trap heat. The phase change energy will give that heat to the different gases, warm them up and cause them to expand, and then they become lighter than the air around them and it rises up and you get convection. Cirrus is particularly an interesting cloud because it's ice that tends to trap heat underneath it. It's a very, very powerful greenhouse gas. So when I say that, what I mean is it's about 200 watts per meter squared compared to carbon dioxide, which is about 4 watts per meter squared. It's not even on the same scale. It's a much more powerful heat trapping cloud than CO2 is, to the point where it makes CO2 relevant unless there's what's called an amplification. And there's a lot of debate in the climate change circles about this. But what I'm talking about is when you get carbonation inside a droplet that's supercooled, how fast, the rate at which it freezes and gives these delta energies to the air has a lot to do with the carbonation in the droplet and the electrical fields involved. Because instead of getting a nice uniform freezing, you get an asymmetry, a different rate change because of the electrical field and because of the acid content in the cloud and it affecting the symmetries of the droplets and how they freeze. So I'm talking about an electrical complexity, and because carbon dioxide is involved, it's a biological complexity as well. And therefore, what I'm talking about is a dampened system. So here today, the subject matter is the 4th La Nina in a row. And the Climate Prediction Center is predicting this La Nina. And so this is significant. And let me see if I can explain. It's not an organized discussion. I'm just kind of freestyling here. But I want to try to explain why this is such a significant thing. In the course of my debates over 25 years and discussions with different people in the climate field, is I've come across professionals that's what they do, is they study this and they study models. And my math background is just very tuned to this. And one of the people that related with or how would you say, interacted with. His name is Ben Cash. He was at Princeton. I think he was at Penn State. And this is I have no idea what he's doing now. I'm just going to quote something that he said to me on a listserv once. And it was basically that we know a lot about how El Nino works, and we can kind of model it. But we don't know a lot about how specific areas, how to predict what's going on and model specific areas. But we have a good idea what's going on with El Nino. And if you look at the fourth La Nina in a row, that's outside of the area of prediction. That's not something that we would see. And the same thing is true, because I want to connect what we think of in terms of weather to what we think in terms of climate. The weather services make these 10-day forecasts, and they've done that since I was a kid. And despite the fact that computers are faster, the models that weather services make are much more complex and robust and have more data coming into them, we're still at 10 days. So what's going on? Why hasn't that weather forecast ability improved at all over a long time? And my answer to that is the sun. And that is because I think that weather has this electrical complexity. Space weather and solar weather also has electrical complexity and influences how clouds behave and then how weather behaves. And so it's impossible to model your 10-day forecast, because after 10 days, the weather from space changes, and it changes, it's garbage in, garbage out. It changes a model's ability to predict what's going to happen in the future. There's just too many inputs that are not being predicted and changing the very behavior of clouds. And so when you look at the sun, it spins around, I believe every 20 days or something like that. And so after 10 days, the side of the sun that's facing the Earth and the sunspots and the coronal holes and all the different things that define what's coming from the sun changes. And what comes from the sun also affects what's called cosmic rays, which also enters into the climate system and affects the Earth. And so the sun is very important in terms of cloud behaviors, and we're just not able, without looking at what's coming from the sun, to predict in 10 days what's going on with weather. So the same thing can be said about the sun and how it acts generally on longer time scales. And in this case, when we start talking about the solar cycle, and there's two parts of the solar cycle. There's the sunspot cycle going through where there's very few sunspots to when there's a high amount of sunspots, and back down to a low amount of sunspot. And that takes about, the one cycle of sunspots from low to high is 10, a little bit more than 10 years, 10 and a half years. But then what produces the sunspot cycle is the sun's magnetic field. And after 10 and a half years, that field reverses and you get a new sunspot cycle, but it's in the context of a reversed solar magnetic field. And so truly, if you want to go a full cycle from the sun turning its magnetic field, it's actually like 21 years, because you go from sunspot minimum to maximum, then it flips, different orientation of the sun's magnetic field, and then you go back to minimum and back to maximum. So what we have right now, over the last 4 years to go with these 4 La Niñas, is the sun with a particular magnetic field orientation having very low sunspots. And those very low sunspots then will affect the cosmic rays. And the reason for that, the cosmic rays come from the Milky Way, and we're oriented in the Milky Way, where we are, and our solar system is. And it's not at a perfect angle. It's at, if you've maybe seen pictures of astronomers shooting what the Milky Way looks like in the sky at night, it's kind of like this. It's at an angle, and because it's not it's not perfectly aligned, then it starts to matter how the sun's magnetic field is oriented and how it deflects out against cosmic rays, that it's unique depending upon whether the solar magnetic field is one way or the other. So here we are in this very special quiet period of the sun with sunspots. At the same time, it's oriented in its particular way, and we're getting very special high levels of cosmic rays. And the cosmic rays then affect how the clouds work in an electrical way. But it's a little bit more complicated than that, because there's also a biological complexity in terms of not just what the electrical conditions are and what lightnings are and what the acoustics of that are around the Earth, but also what the carbonation levels are. And then you start to get into fossil fuels, and you start to get into fossil fertilizers, and you start to get into rivers and how they're changed by dams, and you start to get into deforestation, and you start to get into all these different things, these human activities that affect the carbonation in the oceans, particularly the near-shore oceans in the tropics. So right now, then, when you talk about NOAA's new forecast, which is indicating a fourth La Nina, and you start to talk about what Ben Cash was saying, is that we have a fair idea what's going on with a cycle like El Nino, but we are not very competent in terms of predicting rivers. If rivers are part of these biological feedbacks and the system is dampened, the Earth is essentially alive, then when the biggest cycle starts to act oddly at a cycle that we thought we've had a good confidence in predicting how it's going to behave, and you see these El Niños every 2 to 5 years, and now we're seeing a 4-year stretch of nothing but La Niñas. To me, it's very concerning, and the reason is the math of biological systems is much different than a chaotic system. The example that is often given for a chaotic system is the wings of a butterfly flapping all over. What's not talked about is that butterflies actually migrate by the use of the Earth's magnetic field. So there's a feedback built into the biology of a butterfly. It's a terrible example of chaos theory. It's a better example of a dampened biological system that the Earth really is. And if it's a living system, there's a famous quote in a book by Ernest Hemingway called "The Sun Also Rises," and one of the characters is asked, "How did you go bankrupt?" And the character then answers, "Gradually, but then suddenly." And Hemingway's father was a physician who experienced death as a treater and as a physician often. And I imagine that this was kind of a discussion in the Hemingway household when he was a kid, in terms of how the health of a person was affected as they were dying, and you'd see gradual decline of a patient, and then suddenly they would die. And the Earth, in my view, is again a biological system. And so when you see the biggest feedbacks and the biggest systems that are involved with the Earth, when they're starting to gradually go, then in my view, there has to be some serious concern about there being a sudden change in what's going on in terms of the feedback. And for me, because it's about decarbonation with surface lows, particularly in the tropics, where most of the lightning is, and cold oceans hold more carbonation. As the oceans warm, what you're going to see is decarbonation events from surface lows heading towards the poles, and then this is about neoglacial storms. And I believe that we're seeing with this La Nina, fourth in a row, a gradual change where the feedbacks from rivers and so forth are not healthy, and they're gradually declining. And this sets up for when sudden change occurs and you get these neoglacial storms, the consequences of which is potentially end of civilization, maybe the end of human beings. This is the seriousness of this problem can't be overstated, and the flaws in the state of the science by looking at CO2 as a greenhouse gas and not something directly in cloud microphysics and affected by life in general is just an extraordinary mistake, a horrific mistake in the scientific community. And particularly when you start to get these forecasts coming out from national institutes like NOAA, I just feel I need to comment on it and say, Houston, we got a problem. Our hydrology is drying out in the West, and we don't have a good explanation in the models for why that's so. And I believe an electrical model, absolutely, given the massive dams, particularly on the Rio Grande Santiago, the Colorado itself, which is a dam. So see, if you look back even in time, I think this problem is existed in the 30s when Hoover was built and there was a dust bowl. And then in Ukraine, 12 million people died when a dam was built on the main river there. And then since then, we've had the human use of fossil fertilizers, which is basically taking something out of the inactive part of the biosphere and putting it in the active biosphere, which then affects carbonation in the nearshore oceans. It's a complex problem, and the models aren't capturing what is really going on, what the actual mechanism is. And so now here we have a model predicting the fourth La Nina in a row from NOAA, and it's sort of more or less reporting what's occurring rather than predicting what's occurring. It's not a predictive model, it's a reporting model, and it's not. It's once again it's ignoring this electrical complexity. Okay, so I'm done. I'm encouraged to keep these videos shorter, but this video is about the predicted fourth La Nina in a row and my views why it's occurred. Have a blessed day. Thank you.